Welcome to the 30th lecture of surface engineering. This is going to be a brief discussion on the need for post-carburizing heat treatment or post-nitriding heat treatment. Usually one certainly needs to carry out certain heat treatment, namely the hardening treatment after carburizing. What we must realize is that by way of carburizing, you actually introduce carbon and make the surface ready for hardening. You are dealing essentially with a stock which has very low carbon, 0.1, 0.2% carbon. So even if you subject this whole component to hardening treatment, you may develop martensite, you may enforce martensitic transformation onto the surface, but that martensite will not have adequate strength or hardness because the amount of carbon is inadequate. You require at least about 0.4 weight percent carbon or more to get the optimum martensitic hardness. And it is because of this reason you introduce carbon by carburizing. But then after the carburizing treatment, which is a batch process, you actually when you take the component out after carburizing treatment, you cannot immediately subject it to quenching, simply because, as I said, it's a batch process. Either it's back carburizing or liquid carburizing or some gas carburizing. In all these cases, the chamber is enclosed, components are inside, so you have to break the vacuum or lift it out of the liquid bath or salt bath, or break open the solid mass that forms, the sintered mass that forms after back carburizing. So you have to open the pack and then remove the materials, and so by then they come to room temperature, if not at least to fairly low temperature. So already they are in the any longer in the austenitic range, so they are already in the ferritic range. So you have to bring it to in order to bring it to the martensitic state or martensitic microstructure on the surface, you again have to reheat and then quench. So let's look at as to how we do it. So in this, if we look at the first slide, you realize that, so this is the steel part of the iron cementite phase diagram, and we are primarily concerned, so we are dealing with an alloy which basically is low carbon, 0.2, 0.3% carbon, and in order to introduce carbon, we took it to 930, 940 in that temperature range, in this temperature range, so that carbon can diffuse in faster and deeper. So after that we take it out, and then we when we take out of the chamber, this is what I was mentioning a few minutes ago, that the temperature already drops to fairly low temperature, easily below maybe just a few hundred degrees, maybe 100, 200 degrees, just above room temperature. So that's the temperature range when you are in this in the ferritic zone. So there is no question of transformation ferrite into martensite. In order to do that, you have to again reheat, go to the austenitic zone, and then quench. Then only you can get martensite. So what this is the general guideline for all kinds of heat treatments in steel. Typically for hardening treatment, this is the temperature band, and since we are dealing with low carbon, so this is the region of our interest. So we do actually, we carry out the carburizing treatment at slightly higher temperature. Since we do it at fairly high temperature and the time period is longer, so we generally end up getting a very coarse microstructure, and that's not very good. That's actually detrimental for mechanical properties. So when we reheat to about this temperature, and from there we have to quench fast. And while talking about quenching, what we must realize is that we are aiming a quenching rate which will be at least as fast as this. That means we must avoid the nose, and hence the so-called critical cooling rate, which is the minimum cooling rate that can avoid intersecting the pearlitic or bainitic start line, is the so-called critical cooling rate, and this is what we must adopt. So in other words, we have to adopt some drastic quenching because this time period is very, very small. Now, when we quench, then we convert the surface into martensite. That's our desired microstructural product. And martensite actually can appear either in lath morphology or in acicular or plate morphology. So, this is the typical microstructure that we aim to achieve onto the surface. But we also are aware that the carbon content and cooling rate both actually decrease as we go from the surface to the core. So, if this is the surface and if this is the core, then carbon content is highest here and gradually decreases, and the cooling rate also, whatever the temperature to which we expose is of course highest at the surface, but when we quench, then the cooling rate will be the highest at the surface, and the cooling rate also decreases as we go deeper inside the interior. So, in fact, the cooling rate that we make sure is actually applicable up to a certain depth from the surface and not beyond. So, below this the cooling rate will be lower, and hence we end up getting a microstructure which can be just purely perlitic, coarse perlitic or perlitic, or at the most fine perlite like this. In addition to, when we talk of carburizing, then it's all about martensite. It's all about martensite. The strength comes from martensite, nothing else. But when we talk of nitriding, then of course we have precipitates. And in ultra fine condition, for example, at the very beginning, or if the nitriding period is very small, or if for whatever reason we are able to create a condition whereby we have very high nucleation rate, but very small growth rate. That means we form a precipitate, a nitride, but we don't allow it to grow. So, if we have tiny little precipitates formed all over, then they are not allowed to grow, then some of these precipitates actually may maintain very small size, and at the same time the surface will be at least semi-coherent, if not coherent. But coherence is something we don't quite expect in case of nitride, because the crystal structures are very different than the ferrite. So, if you have two phases alpha and beta, where these two have vastly different crystal structures, you don't expect coherency at the matrix. So, if you don't have coherency, then obviously you don't expect precipitation hardening. But what you certainly expect is dispersion hardening. These nitrides actually offer the strength to the surface by way of dispersing themselves in very fine form. Of course, remember, this is a very high resolution microstructure and transmission electron microscopy microstructure. So, typically these precipitates are very, very small. So, these kind of dispersoids, or so-called precipitates which are incoherent precipitates, will offer OR1 strengthening, and that's why we call it dispersion hardening. So, that's this side on the right is for nitriding, and this column is all for carburizing. We need to take a look and sort of review the situation as to what happens after carburizing. What is the state after carburizing? So, first thing we realize that we have developed a compositional gradation, so which can be easily from 0.2 weight percent to about 0.8, even 1.1 weight percent of carbon at the surface. So, from the core to the surface, so if this is the sample and if this is the core, so from the core to the surface, particularly at the top layer, we have a gradation of composition. We also desire a gradation of microstructure, because we want full martensitic on the top surface and certainly fine perlitic at the core, so that we actually maintain very high toughness at the core and very high wear resistance at the surface. So, both compositional gradation and microstructural gradation are desired. Now, after carburizing, well, I am sorry, this actually should be higher. almost above 930, 950. Of course, carburizing is possible at 800 range as well, 830, 850 range as well. But usually for larger components, you expose to 930, 950 temperature range for about 6 to 8 hours. What you develop throughout is a very coarse microstructure. So the typical crystallite size would be fairly coarse. Now, this is good for converting into martensite, but not so good for introducing or retaining toughness in the core. So this core microstructure is not is to be broken and is to be converted into finer microstructure. So we need grain refinement. And so for all these reasons, coarsened structure and taking care of the gradation of microstructure and composition, we require certain post-carburizing heat treatment so that we improve and refine the microstructure, we achieve desired hardness and mechanical properties, we break the cementite network. Now, generally, if you go to 0.8 and above, or let's say 1% carbon or something, then the austenite will be covered by a cementite network like this. So this will be your Fe3C if the composition of the steel is hypereutectoid, that means greater than 0.8% carbon. So this cementite network actually is very hard and also very brittle. So if you already create such network, then you cannot do machining, you cannot do any post processing. So this is not desirable, and also it actually creates a sort of a conflict with the martensitic post heat treatment martensitic microstructure. So in order to break this hypereutectoid microstructure or cementite network, we also need a follow-up heat treatment, and we also need a final tempering of the component, because if otherwise the fully hardened microstructure is very hard and brittle. So in order to actually match this difficult demands of having perlite at the core, martensite at the surface, and yet there should not be any very large grain size, and also should not be a lot of stress gradients, but of course we want residual compressive stress on the surface and high hardness. And yet if we want some post-processing machining or other treatments, so we want certain amount to restore certain amount of machinability. So keeping all these things in mind, we may require a post-processing heat treatment, but that's a final tempering treatment. But in general, if we now imagine that this is a component that we have carburized, and the core is 0.2%, and the surface is let's say 1% carbon. So obviously we are talking about as if two different steels merged into one. So for this 1% carbon, we do harden from above the AC1 eutectoid temperature, but for 0.2% we harden or normalize or whatever, we do it from above AC3, which is fairly higher than that. So how do we match these two conflicting situations? We do it in this way. So first of all, this is the hardening treatment. This is the typical carburizing treatment. So after carburizing, we bring it to room temperature. Then we want to carry out typical hardening treatment. So if we do a single stage hardening treatment, then we have to go to above the eutectoid temperature and then quench. But since we are dealing with two different steels almost merged into one, the surface is at a fairly high carbon content and core is at a low carbon content. So we now have to, so this single treatment is not adequate. So this is not adequate. So then what we do is, first we take care of the core, because the core is at a higher carbon content. So we heat to above AC3. So so if we do separately, then we might do something like this, that we can heat treat. So first we heat the surface to much higher temperature, and then we can repeat a similar hardening treatment for the surface, which could be either between AC1 and AC3 like here, or just above AC1. And when we quench, in all the cases we actually are quenching, sharp quenching, so that there is no time lag, and we come to room temperature drastically, so that we actually are able to convert austenite into martensite. But when we do it, we can't do it separately for two different parts of the component. So in the sense, we cannot separate the component into two parts and then carry out two different treatments. So all these are hypothetical situations and not quite applicable, because we are dealing with a single component. Now, in order to actually carry out the heat treatment to convert austenite into or obtain martensite onto the surface, we do a composite treatment like this. So the component is the same. So we first heat to above AC3 and then normalize. We don't necessarily quench, we just cool in air, still air, so that the coarse microstructure at the surface now converts into fine pearlitic or fine ferritopearlitic microstructure, good enough to give us fair amount of toughness. We don't want to develop very high hardness at the core. So the core is not meant for very high hardness, it's only meant for providing toughness. Now we reheat, so we bring to room temperature and then we reheat, but we don't reheat to above AC3, we reheat only above AC1, because the microstructure here is hypereutectoid, so 0.8 and above. So this does not require heating above ACM, it requires heating only above AC1, and from AC1 temperature, just above AC1 temperature, we need to quench. So in the first leg, if this is the first leg, which is meant for normalizing, and what we get is fine pearlite. In the second leg, when we heat from above AC1 and not above AC3, what we do is harden. And by hardening, we convert austenite into martensite. But actually this martensite, what we believe is to be martensite, is not 100%. If it's not 100%, then what else does it have? It is likely to have retained austenite, which is not very conducive for dimensional accuracy or the volume of the material, because during heat treatment or during subsequent use in operation due to mechanical activation, this retained austenite can convert either into bainite or into martensite, depending on the path it follows. So in either case, there is a possibility of, again, expansion or contraction, volume change, and that means it may develop cracks onto the surface, which is what is undesirable. So after the quenching, after the final quenching, we actually can carry out tempering to convert part of the martensite into tempered martensite, and then we carry out the final hardening, and then we do a final tempering at a lower temperature, which is only for stress relieving. So by and large, what we need to understand is that carburizing is a treatment, is a process to introduce carbon. So now you make it ready, you convert a 0.2% carbon steel and make it ready with certain enrichment of carbon up to the level of 0.8, up to 1% carbon. And with such enriched carbon enriched surface, what we now need to do is to take it to only above AC1 and then quench and convert into martensite. Then it's hardened. Then we can talk about all the improved mechanical properties. But the core, since it is at 0.2%, we need to heat above AC3 and then air cool, which is normalizing, to get fine pearlitic microstructure. So what all we have discussed briefly here, we have discussed the post-carburizing heat treatment that's needed because of the requirement to develop the complex graded microstructure, and also because we have widely varying composition from the surface to the core. We don't need a similar treatment for nitriding because the hardening is coming not from martensite, it is coming from nitrides which are already formed during the nitriding process itself. So the material is ready for use just after the nitriding treatment. The carburizing treatment, unfortunately, is a batch process. It's not a continuous process because you need to break the atmosphere, you need to break the carbon-rich atmosphere and then take it out, and then you do carry out the heat treatment. So it cannot be a continuous process, except in very rare cases of some gas carburizing treatments. The microstructural gradation we need because we need martensite, predominantly martensite, to or at the end maybe tempered martensite, predominantly martensitic or tempered martensitic, to all the way to simply pearlitic or ferritopearlitic microstructure. The composition does play a role. If you are dealing with alloy steel, you treat in a way. If you deal with plain carbon steel, then obviously the temperature and time requirements are a little different. And we certainly need a final tempering treatment so that the stresses are relieved and some amount of machinability is restored. Now, it is also time that we take an overall view of all the possibilities of hardening that we have discussed so far with regards to primarily steel. So we have discussed three types of approaches: hardening, carburizing and nitriding. Hardening is without change in composition, so it's simply microstructural modification. Carburizing and nitriding is thermochemical treatment where we change the composition of the surface. In carburizing we introduce carbon, in nitriding we introduce nitrogen. So the components and the parts that we actually subject for such treatments need not be exactly the same type. For example, compositionally one can easily say that for hardening we actually require carbon rich or at least the component should have adequate carbon, easily around 0.4% carbon for minimum, whereas carburizing nitriding is done with very low carbon. The parts and their utilities will determine what kind of treatment you actually take, and the effectiveness of the treatment will depend upon the temperature, time, atmosphere and various surface preparation methods that you adopt. The heat treatment is required only for carburizing, and in hardening treatment is itself a heat treatment process. So there is no separate heat treatment required, there is no post-processing hardening treatment required for hardening, but carburizing does require one. The strengthening mechanism in hardening carburizing is the same, is the martensitic hardening, but in nitriding it's different, it's the presence of these nitrides. The microstructural variation from top surface to the along the cross-sectional plane is a smooth one, is to be understood, is to be developed carefully so that the final purpose is served. But end result or the end aim is hardness, lowering of friction coefficient, improvement in wear resistance, and in some cases even corrosion resistance for nitriding cases. So we actually at the end of these last few lectures, maybe starting from 21st or one of those lectures, wherein we started discussing all these hardening processes. And in fact, even before hardening processes, we discussed the shot pinning, shock pinning processes. So now is the time for all of you to sit down and take a stock of what all you have learned. What are the purpose, what were the purpose, what were the end results, what microstructure, what mechanism of strengthening, how do they compare with each other in terms of process difficulty or ease, the process parameters, time, temperature, atmosphere, various other implements necessary, what's the level of property changes that you bring in, what are the merits, what are the demerits, and finally the applicability for various industrial practices. So I hope you have picked up some good threads for self-study, and I would definitely implore upon you that lectures are only a supplementary tool, are only to expose you to the subject. but in order to derive the required knowledge, you must do self-study and refer to the textbooks given at the end of the lecture series. Thank you very much.